In this video, we'll be discussing the Moore concept. So let's get into it. Now, you remember that matter is made up of particles like atoms, molecules, and ions. But we can also talk about particles like elements. Now, these particles are too tiny to be counted. And so how do we count the number of atoms, molecules, ions, or elements? This is where we have the concept here, which is the Moore concept. So this Moore is pointing to the number or the amount of substance containing 6.022 times 10 to the power 23 particles. And this number here, which you've seen, is actually called Avogadro's number or Avogadro's constant. So make sure that you understand this number. When you're trying to understand the number of atoms, molecules, ions, or elements, we use what we call the Moore. So the Moore is an expression of the amount of particles that we have. And each Moore is pointing to the amount of substance containing these particles, 6.022 times 10 to the power 23. Now, there are symbols that you need to be familiar with. N is pointing to the number of moles. And when you're talking about Na, this is pointing to Avogadro's constant. Or Avogadro's number. And you know that this number is 6.022 times 10 to the power 23. Now, N is actually pointing to the number of particles. So when we have these three, we can actually find either the number of moles, or if we're trying to find the number of particles. So if we have the number of moles, we can calculate the number of particles, because this Na, Avogadro's constant, is actually constant. It is this figure. Now with this, there are some few formulas that you need to be familiar with. This N, which is the number of moles, is equal to the number of particles over Avogadro's number. Or sometimes you can calculate the moles using this particular formula. Moles is equal to mass over Mr. So this is mass, and this is the relative molecular mass. So make sure that you understand these two formulas, because they are quite important. If you are trying to find the number of moles and you have the number of particles, you can use this particular formula here. If you are trying to find the number of moles and you have the mass and you can find the relative molecular mass, then you can use this particular formula. So make sure that you understand these concepts. Now, there are also what we call the gas volumes. Now, these are also important. You understand that since we're dealing with moles here, 1 mole is equal to 22.4 decimeter cubed. That is if you are dealing with the standard temperature and pressure. If you are dealing with the room temperature and pressure, this 1 mole is equivalent to 24 decimeter cubed. That is at room temperature and pressure. So make sure that you understand this information as well, because it's going to help you as you deal with problems on the Moore concept. Now, here's a question for you. How many molecules are present in 0.25 moles of water? So how many molecules? So when you're talking about molecules, you're talking about the number of particles. So because molecules are part of those particles, then you're talking about the number of particles. So how do you calculate this one? Well, again, you go back to the same formula. Mole is equal to the number of particles over Avogadro's number. So in this case, you can just make n the subject of the formula. You're going to have the number of particles is equal to the number of moles times Avogadro's number. So in this case, we're going to say, how many moles do we have? Notice we have 0.25 moles times, what is the Avogadro's number? It is 6.022 times 10 to the power 23. So when you multiply this, you're going to have 1.505 times 10 to the power 23 molecules. So this is how you find the number of particles. And remember that 1 mole of any substance contains Avogadro's number of particles, which is this particular figure here, 6.022 times 10 to the power 23. Now the next thing that we can talk about is what we call the relative masses. And in this case, we are talking about the relative atomic mass. So what is the relative atomic mass? Now, when you're talking about the relative atomic mass, this is the weighted average mass of an atom when it is compared with 1/12 mass of carbon-12 atom. So whatever average mass you're going to get of an atom, you compare it with 1/12 mass of carbon-12. So for example, the relative atomic mass, which is written like this, of hydrogen is actually 1. So this means that the mass of hydrogen is greater when it is compared with the 1/12 mass of carbon-12. And here we can look at another example. Let's say this is oxygen. The relative atomic mass of oxygen is actually 16. So it is 16 times greater than the 1/12 mass of carbon-12. Or we can also talk about sodium. When we look at sodium, we see that it has 23, and it means that it is 23 times larger than the 1/12 mass of carbon-12. So basically, when you're talking about the relative atomic mass, it is essentially the mass number of an atom. Now, the other thing that we can talk about is what we call the relative molecular mass. So what do you think is the relative molecular mass? Now, this is the sum of relative atomic masses in simple terms. The sum of the relative atomic masses. So what does it mean? Well, this relative molecular mass is actually written as mR. So this is the relative molecular mass. So let's say, for example, we want to find the relative molecular mass of water. So how do we deal with that? Remember, this is the sum of the relative atomic masses. So the first thing that we need to understand is that we need to look at the atomic mass of each element that we have, or each atom that we have here. So in this case, we have hydrogen and oxygen. So what is the relative atomic mass of hydrogen? Remember that it is 1. But how many hydrogen atoms do we have here? We have 2. So this is going to be 2 multiplied by the relative atomic mass of hydrogen, which is 1. And since we are talking about the sum, then this is going to be plus. And what is the relative atomic mass of oxygen? Remember that it is 16. but we have only one oxygen atom here. So this is going to be 1 times 16. So this is going to give us 18 in total. So 18 is the relative molecular mass of water. Now we can also try another example. Let's try carbon dioxide. So what is the relative molecular mass for carbon dioxide? Now again, you look at carbon itself here. What is the relative atomic mass for carbon? Well, you have 12 as the relative atomic mass of carbon, but how many carbon atoms do we have here? Only one. So 1 times 12. And then we're going to add oxygen here. We have 2 oxygen atoms. So multiplied by its relative atomic mass, which is 16. And there we're going to have 44 as our relative molecular mass. So make sure that you understand how you deal with the relative molecular mass. But the last thing that we can talk about here is what we call the relative formula mass. So what is the relative formula mass? How would you say? Well, when you're talking about the relative formula mass, usually it is another version of the relative molecular mass, but it is usually used for the ionic compounds. So compounds that are ions, like let's say sodium sulfate. This is an ionic compound in the sense that you have 2 ions here forming this particular compound. So how do you find the relative formula mass of this particular compound? Well, it's simple again. You just follow the same principle which you use when you're trying to find the relative molecular mass. So here we're going to have sodium here is 23. So this is the relative atomic mass for sodium, but we have 2 sodium atoms. So this is going to be 2 multiplied by 23. And we're going to add, here we have sulfur. Now for sulfur, its relative atomic mass is actually 32. And so this is going to be 1 sulfur atom times 32. And then we are going to add, here we have 4 oxygen atoms multiplied by its relative atomic mass, which is 16. And so we are going to get 142 as the relative formula mass. So make sure that you understand how to deal with problems on the relative atomic mass, the relative molecular mass, and the relative formula mass, which are quite related in some way. Now, let's look at more calculations. Remember that when you look at the formula, mole is equal to mass over Mr, or the relative molecular mass. This is an important formula. So for example, we can give an example. When calcium carbonate decomposes on heating, this is going to produce calcium oxide plus carbon dioxide. Now, let's say that the mass of calcium carbonate is actually 50 grams. Now the question is, find the number of moles in these 50 grams of calcium carbonate. Find the number of moles. So how do you deal with this particular problem? Now, since you are dealing with calcium carbonate, notice that you have the mass, which is 50 grams here. So all you have to do is find the relative molecular mass of calcium carbonate. You have the mass, and then you can use this formula. Mole is equal to the mass, which is here, over the relative molecular mass, which you're going to find. And that is going to give you the number of moles. So let's go ahead and do that. Now, when you look at calcium carbonate here, you realize that its relative molecular mass is going to be, calcium here is actually 1 by 40, and the carbon here is going to be 1 by 12, and the oxygen here is going to be 3 by 16. So when you do the math here, you're going to get 100. So this is the relative molecular mass of calcium carbonate. Now that we have the relative molecular mass, we can go ahead and find the number of moles. So make sure that you write the formula properly. Mass over the relative molecular mass. So this is going to give us, what is the mass here? Notice that the mass is 50 grams. So we're going to write 50 grams here, and the relative molecular mass is actually 100. So here we're going to discover that the final answer is going to be 0.5 moles. And so this is our answer. Now, another example which we can give on the same topic. Let's say that we have magnesium reacting with hydrochloric acid, and this is going to give us magnesium chloride plus hydrogen gas. And let's say that we have 12 grams of magnesium which reacts with hydrochloric acid. So this is going to be 12 grams. So find the number of moles of magnesium which is used in this case. So how do you deal with this particular problem? Now make sure that when you're dealing with problems on the mole concept and you have an equation, make sure that the equation is balanced. So this is not balanced, you can put a 2 here and the equation is balanced. Now, since we're just dealing with magnesium here, and we have 12 grams of magnesium, we can only find the relative molecular mass of magnesium and then go ahead and find the number of moles. Now, the relative molecular mass for magnesium is actually 24. So we can go ahead and find the number of moles. And this is going to be, what's the mass here? Notice that it is 12. So it is 12 over the relative molecular mass is actually 24. So this is also going to give us 0.5 moles. So this is our answer. Now sometimes when you're dealing with mole of gases, remember that you have 1 mole which is equal to 24 decimeter cubed. Now this means that sometimes you might be given the number of moles. Let's say that the number of moles of carbon dioxide at room temperature and pressure is actually, let's say, 2 moles. So find the volume of carbon dioxide at this particular temperature. So you can just use the mole ratio here. 1 mole gives you 24 decimeter cubed. How much volume are you going to get for 2 moles? So in this case, you just have to cross multiply. X is going to give you 48 decimeter cubed. And so this is the volume of carbon dioxide having 2 moles and at room temperature and pressure. Now here is a second concept that we can look at. It is actually stoichiometry. How do you deal with problems where you have an equation and then you get the information or deduce the information from that particular equation? Because this is the quantitative study of reactants and products using balanced equations. When you're dealing with equations, how do you calculate the number of moles or mass or something like that? So there are some steps that you need to be familiar with. So here are the steps that you need to keep in mind. First, make sure that you write a balanced equation. And after you've written a balanced chemical equation, then find the number of moles. Third, make sure that you use the mole ratio. I'm going to show you how to do that. And lastly, you can convert what you have to required quantity. So convert to required quantity. So make sure that you understand these 4 steps. So let's go ahead and look at some problems. So how many grams of water can be produced when 4 grams of hydrogen reacts with oxygen? When 4 grams of hydrogen reacts with oxygen, how many grams of water are going to be produced? Now, remember the 4 steps. The first thing is make sure that you write a balanced chemical equation. Here, hydrogen is reacting with oxygen to produce water. So this is an equation, but make sure that it is balanced. So you can put a 2 here and a 2 there, and the equation is balanced. Next, since you have the mass of hydrogen like this, you can actually find the number of moles of hydrogen. So how do you find the number of moles of hydrogen? Well, if you have the mass, you can use this formula: mole is equal to mass over the relative molecular mass. So here, when you look at the mass, notice that it is 4. So it is 4 over. Notice that here you have 2 hydrogen atoms, and the relative atomic mass of hydrogen is actually 1. So it is 2 times 1, you get this mixture, or the relative molecular mass, and so it is going to be 2. So make sure that you do not include this number, the coefficient, when you're trying to find the moles. So this is going to give us 2 moles. Now the next thing is to find the mole ratio. Since you are interested in finding the number of grams of water, then how do you get the number of grams of water here? Well, you can't have the number of grams if you don't have the number of moles of water, because it will be easy for you to find the relative molecular mass. But for the moles, that's why it's important to use the mole ratio as the next step here. Since you have the number of moles of hydrogen here, you have 2 moles, then you can compare the 2 here. Here, you will notice that you have 2H2 and you are comparing it with 2H2O. So these are the 2 things that you are comparing. Since you have the number of moles of hydrogen here, you are going to see that these coefficients here are trying to show you the number of moles. So you can say 2 moles of hydrogen will give you 2 moles of water, because these are the moles that we have. And then we have 2 actual moles which we calculated for hydrogen. How many moles are we going to get for water? So this is going to be 2x is equal to 4, and then x is equal to 4 over 2, which is 2. So again, we're just going to get 2 moles of water. So this is how we find the mole ratio. And the last thing that we can do here is to simply find the mass of water. Since we have the number of moles of water, we can go ahead and calculate the mass of water. Now remember, the formula is the same. Mole is equal to mass over the relative molecular mass. But we are finding the mass here. So the number of moles is actually 2, and the mass is unknown, which we are looking for. And what is the relative molecular mass for water? Notice that here hydrogen is 2 times 1, and then plus oxygen here is 1 times 16. So this is going to give us 18. So we're going to have 18 here. So the mass is going to be 18 by 2 is 36 grams. And so this is the mass of water. Now the other question is benzoic acid, which is actually C6H5COOH, burns in oxygen, and obviously it is going to form carbon dioxide and water only, because this is a combustion reaction. The first question is, how can you write a balanced chemical equation for this particular reaction? Well, first of all, for this question, we're going to say benzoic acid reacts with oxygen, and this is going to produce carbon dioxide and water. So how do you balance this particular chemical equation? So when we put a 2 here, we are going to have 14 carbon atoms on this side, because you have 2 here and then times 6 is equal to 12. Then 2 affects this C here, so this is going to be 14, which means that we can put 14 here to balance it here. And then that means that hydrogen is now 12, because 2 times 5 here is actually 10, plus 2 affects this H here, which is 2, so this is going to be 12, which means that we can have a 6 here to have 12 hydrogen atoms, but then that affects the oxygen atoms here, because here we're going to have 28, 14 affects these two, so 28, and then this is going to be 6 oxygen atoms, so this is going to be 34. So here we can put 15, so this is going to be 30, and then these 2 oxygen atoms times 2 is actually 34. So the equation is actually balanced in this way. Now the next question is, if 0.1 mole of benzoic acid reacts, calculate the volume of carbon dioxide produced at room temperature and pressure. So how do we find the volume of carbon dioxide? Now, we can only find the volume of carbon dioxide produced if we have the number of moles of carbon dioxide. And in this case, since we have the number of moles here of benzoic acid, which is 2, let's go back and use the mole ratio, because when you look at the steps there, the first thing is write a balanced chemical equation, which we've done. And the second thing is we have to find the mole ratio. So in this case, 2 moles of benzoic acid will produce 14 moles of carbon dioxide, right? And then this means that actually you can reduce this. So when you reduce this, it is actually 1 mole of benzoic acid to 7 moles of carbon dioxide. Then here we have 0.1 moles of benzoic acid. How many moles is it going to give us? So we have X. So in this case, 0.1 times 7 is going to give us the number of moles of carbon dioxide produced. And so this is going to give us the number of moles of carbon dioxide will be 0.1 times 7, which is actually 0.7 moles of carbon dioxide. Now, to find the volume of carbon dioxide, notice that it says that this is at room temperature and pressure. So this means that when you go by that same principle, 1 mole is equal to 24 decimeter cubed, because remember we are finding the volume. So 0.7 moles is going to give us how much of the volume? So this is going to be 0.7 by 24. How much are we going to get? Well, if you do the math here, the volume of carbon dioxide will be, so this is 16.8 decimeter cubed. And so this is the volume of carbon dioxide produced at room temperature. Now the next thing that we are going to look at is what we call the limiting reagents. What does that actually mean? Well, first of all, let's look at an example and then you're going to see what it actually means. So let's say calcium carbonate reacts with hydrochloric acid and then it produces calcium chloride plus water plus carbon dioxide. Now this can be balanced by putting a 2 here, and yeah, that is balanced now. Now if 10 grams of calcium carbonate and 8 grams of hydrochloric acid react, then identify the limiting reagent. What would you say? Which one is a limiting reagent? Now, a limiting reagent is a reagent which will cause the reaction to stop because it has been used up completely. If you have some amount of substance that remains between the reactants, then that is not the limiting reagent. The limiting reagent must be used up quickly and sooner than the other reagent. So the one which is used up first and therefore causes the reaction to stop, that is what we call a limiting reagent. Now remember that here we have 10 grams of calcium carbonate and 8 grams of hydrochloric acid. So let's go ahead and find the number of moles of calcium carbonate and hydrochloric acid. Now for calcium carbonate, you remember this is going to be, so the number of moles of calcium carbonate will be, what is the mass? Notice we've been given 10 grams as the mass, and if you calculate the relative molecular mass of this calcium carbonate, you're going to get 100. So this is going to give us 0.1 moles. Next, we can find the number of moles of hydrochloric acid. Now, the mass of hydrochloric acid we've been given, it is 8, and then if you find the relative molecular mass of hydrochloric acid, you're going to get it should be 36.5. Now 8 over 36.5 is actually this is going to be 0.219 moles. Now, because calcium carbonate has less number of moles, this is 0.1, than hydrochloric acid, which has 0.219 moles, then because this is smaller than this, then the one which is smaller is used up first before the one which is larger. So this is how we identify a limiting reagent, because it has less number of moles than the other reagent, and therefore that's how we detect or ascertain which is a limiting reagent. And so that is our answer for that particular question. So make sure that you understand, if a reagent has less number of moles, then it is probably going to be used up completely before the other reagent, and therefore that reagent with smaller number of moles is going to be the limiting reagent. Now we can also try to find, this is question 2, the mass of carbon dioxide produced. So how do you find the mass of carbon dioxide produced? Now, because you are talking about the mass of carbon dioxide produced, the first thing that you need to do is you can find the moles of carbon dioxide by using the mole ratio. Since the number of moles of calcium carbonate is actually 0.1, then you can use the mole ratio here to find the number of moles of carbon dioxide. So notice that you have 1 here and then you have 1 there. So 1 mole of calcium carbonate is going to give you 1 mole of carbon dioxide. Then how many moles of carbon dioxide are you going to get for 0.1 moles of calcium carbonate? So this is going to give you 0.1 moles of carbon dioxide. So we can use these moles to find the mass of carbon dioxide. So let's go ahead and do that. So the number of moles is equal to mass over the relative molecular mass. So here you have 0.1 as the number of moles, and we're looking for mass, and the relative molecular mass for carbon dioxide is actually 44. So when you do the math here, you're going to discover that the mass of carbon dioxide is actually 4.4 grams, and so that is our answer. The next thing that we are going to talk about is how to write the empirical formula. Now, first of all, we have to look at the steps, and then you're going to discover what this empirical formula is. So first, convert masses to moles. Convert masses to moles. So when you've been given masses, make sure that you convert them to moles. Second, you divide by the smallest number of moles. So divide by the smallest number of moles. So we're going to see how to do that. Third, and then obtain the ratio. And then lastly, you can write the empirical formula. So let's go ahead and look at some examples. And make sure that you remember these steps because they are very important. Without this, you cannot write the correct empirical formula. So let's say that a compound contains, and then we're going to say 40% sulfur, and then it also contains 60% oxygen. Now find the empirical formula using the information provided. So how do you deal with this particular problem? Now, the first thing to understand is that according to the first step, you have to convert these masses to moles. Now, notice that we have percentages here. We have sulfur, which is 40%, and then we have oxygen, which is 60%, which means that the total percentage is actually 100. So, for sulfur, this 40% is going to be treated as the mass. So, assuming that you're trying to find the number of moles, remember that moles is equal to mass over Mr, or the relative molecular mass. So, assume that the percentage here is the mass. So, if you're trying to find the moles here, you're going to have 40 over 32, because 32 is the relative molecular mass of sulfur. You're going to do the same for oxygen. Here you have 60%, which is going to be considered 60 grams. And then this is over 16. So this is going to give you 1.25 moles for sulfur, and you're going to have 3.75 moles for oxygen. Now, when you look at these two numbers here, notice that you are going to have the ratio of 1.25 to, this is 3.75. So you can divide by the smallest. So here you can say 1.25 and then 1.25. So this goes into this once. So you're going to have 1, and then this is going to give you 3. So 1 to 3 is the ratio that you're going to get there. Now remember, 1 is for sulfur and 3 is for oxygen. In other words, you have 1 sulfur atom and 3 oxygen atoms. When you put them together, you're going to have, this is sulfur, and then you have oxygen 3 here, because you have 3 oxygen atoms here. And so this is the empirical formula for these two elements. The hydrocarbon contains, let's say it has 85.7% carbon and 14.3% hydrogen. So how do you find the empirical formula for these two elements? So again, make sure you understand that those percentages should represent the mass. So for carbon, this is what you're going to have, because you have to change the masses, which are percentages in this case, to moles. So you're going to have 85.7 over 12, which is the relative molecular mass of carbon. And then for hydrogen, you're going to have 14.3 over 1. So this is going to give you 7.14, and this is going to give you 14.3. So you're going to write the ratio. So this is going to be 7.14 to 14.3. Now when you divide by the smallest, 7.14, and here is 7.14, this is going to go into that once, and then you're going to have the ratio of, this is 1 to 2. Now this one is for carbon and the 2 is for hydrogen, which means that you're going to get carbon and then 2 hydrogens. So this is the empirical formula for you. Now you can also say, let's say a compound contains 40% carbon and 6.7% hydrogen and 53.3% oxygen. So how can you write the empirical formula? Now remember that this is going to be 40 over 12, and this is going to be 6.7 over 1, and this is going to be 53.3 over 16. So you're going to get 3.33, and here you're going to get 6.71 over 1 is actually 6.7, and you're going to get here 3.33. So when you make the ratio here, you're going to have 3.33 to 6.7 to 3.33. So when you divide by 3.33 here, let's delete this. This 3.33 into 3.33 is 1. Here it is going to go in twice. So you're going to have 1 to 2 to 1. Now this means that the first one is for carbon and the 2 is for hydrogen, which is 2 here, and again you have oxygen. This is the empirical formula for this particular question. Now the next thing that we are going to talk about is actually the percentage yield. Now usually when you're talking about the percentage yield, you're talking about the percentage that you're going to get when you divide the actual yield by the theoretical yield. So percentage yield is actually the actual yield over the theoretical yield multiplied by 100%. So in other words, it's like when you're doing farming and you're trying to determine how many bags of maize you are going to harvest at the end of the farming season. So you may have a theoretical yield where you say that I'm gonna get 20 bags at the end of the farming season, but when you harvest, you actually find that you get 15 bags. So the percentage yield will be the actual yield, that is the real harvest that you get, over the theoretical yield, that imaginative yield that you had before the harvest, and then multiplied by 100. That is the percentage yield that you are going to get. And the percentage purity is actually almost the same as this. What it means is this is talking about purity. So it is this is percentage purity. It's going to be the amount of the pure sample that you have over the total sample, and then you multiply that by 100%. So these are important formulas that you need to be familiar with when you're dealing with the percentage yield and the percentage purity. So the same is true now for chemical reactions, where you know that we're going to produce this amount of this particular substance. We're going to produce this volume of carbon dioxide or this mass of hydrogen gas. So you may have a theoretical yield where you just have an expectation, it is the expected yield, but then when the reaction is complete and you measure the volume or the mass, you actually find that the actual is slightly less than the theoretical yield that you have. And so you can now calculate the percentage yield by making sure that you get the actual yield over the theoretical yield multiplied by 100%. So let's go ahead and deal with some problems on the percentage yield. So let's say that we have ethanol, and this is the reaction that we are going to have. This ethanol is actually broken down to these products, and let's say that we have 46 grams of ethanol used, and we have 18 grams of ethene collected. So this is ethene. So calculate the percentage yield in this particular reaction. So how do you deal with that? Now, what you need to understand is that it is stated here that 18 grams of ethene is collected. Now that means this is the actual yield. So all you have to do is find the theoretical yield of ethene so that you can calculate the percentage yield. Now it's very easy to calculate the theoretical yield. All you have to do is find the relative molecular mass of this particular compound, which is ethene. And so when you do that, you're going to see that you have 2 times 12 for carbon, plus you have 4 times 1 for hydrogen. So 2 times 12 is going to give you 24, plus 4 there, you're going to get 28. So 28 is the theoretical yield. So to go ahead and find the percentage yield, you're going to say the percentage yield here is, so the percentage yield is going to be the actual yield, which is 18 grams, over the theoretical yield, which is 28 grams. And this is going to give you 64.3%. And so this is the percentage yield. Let's look at another example. Let's say a student heated, let's say 5 grams of impure calcium carbonate. So this is heated. And you know when it is heated, it is going to be a reaction like this. Calcium carbonate, and then you're going to have calcium oxide plus carbon dioxide. Now, what is collected here is that you have 1.76 grams of carbon dioxide produced. So 1.76 grams. So the first question is, how do you calculate the number of moles of carbon dioxide? Well, this is very easy. The number of moles of carbon dioxide will be the number of moles carbon dioxide is equal to, what is the mass of carbon dioxide? It is 1.76 grams. And then what is the relative molecular mass of carbon dioxide? Well, you're going to see it is 44. So here you're going to get 0.04 moles of carbon dioxide. Now, the next question is, how many moles of calcium carbonate are decomposed in this particular reaction? Well, to find the number of moles of calcium carbonate which are decomposed in this reaction, since you have the number of moles of carbon dioxide here, which is 0.04 moles, you can still use the mole ratio to find the number of moles of calcium carbonate decomposed. So you have 1 calcium carbonate being decomposed to the mole ratio of carbon dioxide here is 1. So for carbon dioxide 0.04, it is going to give you how many moles? So you see that still going to get the same number of moles, which is 0.04 moles of calcium carbonate. So that is how you calculate the number of moles. Now, what is the mass of pure calcium carbonate? Since you have the moles here, which is 0.04, it's very easy to find the mass. Mole is equal to mass over the relative molecular mass. So you have 0.04 as the number of moles, and then mass is what you are looking for. The relative molecular mass of calcium carbonate is actually 100. So the mass is going to be 100 times 0.04, which is actually 4 grams of calcium carbonate. And that's the answer. Now, the last question on this one is find the percentage purity. Now, when you're talking about the percentage purity, you're talking about the pure sample over the total substance or sample multiplied by 100%. Now, in this particular case, the pure substance, notice that we found the mass of pure calcium carbonate, which is 4. We've just found it. But you have also these 5 grams of impure calcium carbonate. So you have the pure calcium carbonate of 4 grams and the impure calcium carbonate of 5 grams. So you can use those to find the percentage purity. So this is what we are going to say. The pure calcium carbonate is actually 4 grams and the impure is actually 5 grams, and this is multiplied by 100%. And so this is going to give us 80% as our percentage purity, and this is our answer. Now you can also talk about how to calculate the concentration. Now, when you are calculating the concentration, it is actually, concentration is equal to the number of moles over the volume of the substance given. So that's the general formula that we use when we are trying to calculate the concentration. So let's go ahead and look at some examples. So let's say calculate the concentration if 8.5 grams of, let's say, sodium hydroxide dissolved in 500 cubic centimeters of water. So how do you find the concentration? Now, the first thing that you need to do is to find the number of moles of sodium hydroxide. And in this case, it's quite easy. So the number of moles would be, so this is sodium hydroxide, mass, which is 8.5 grams, over the relative molecular mass of sodium hydroxide is actually 40. So we're going to have 40 here, and this is going to give us 0.2125 moles. Now, the next thing that you need to understand is that this volume here, which we've been given, should be converted into decimeters. Make sure that you convert it into decimeters. So when you convert this volume into decimeters, you're going to see that, because if you remember the ratios here, 1000 cubic centimeters is actually equivalent to 1 cubic decimeter. So which means that if you try to convert 500 cubic centimeters to x, you're going to get x is equal to 0.5 decimeter cubed. Make sure that you understand how to do these conversions. So with this information, we can go ahead and find the concentration. So let's make sure that we understand this. So the number of moles, so here N is equal to 0.2125, and the volume is actually 0.5 decimeter cubed. So let's go ahead and find the concentration. So the concentration is going to be the number of moles over volume. So in this case, the number of moles is actually 0.2125 over 0.5 decimeter cubed. So this is what we are going to have. And so when you use your calculator, you are going to get, so this is what you're going to get, 0.425 moles per decimeter. So make sure you pay attention to the units here, moles per decimeter cubed. So make sure that you understand that. Now, sometimes you might be required to use titration to calculate the concentration. And in this case, the formula that we usually use is C1 V1 is equal to C2 V2. So this shows that concentration 1 and volume 1 is equal to concentration 2 and volume 2. So let's say we have 100 milliliters of 3.0 concentration of an acid, and when this acid is diluted to 500 milliliters, what's the new concentration? How can you find the new concentration? Now here you just have to collect the data. Concentration 1 is actually here. So this is the first concentration, and then volume 1 is actually 100, because this is volume 1. And concentration 2 is what we are looking for. Volume 2 is actually 500. So how do you find concentration 2? So all you have to do here is just do the substitution method here using the same formula which is here. So concentration 1 is actually 3 and volume 1 is actually 100, and concentration 2 is what we are looking for. Volume 2 is actually 500. So this is going to be 3 by 100 is 300, which is going to give us 500 concentration 2. And so we can solve for C2 there, and when we do that, C2 is going to give us 0.6 m, which is molarity. Now, one last thing which I would like us to talk about is percentage by mass. Now, this is pointing to the percentage by mass of an element within its compound. So let's say, for example, we have water. Now, when we have water, what is the percentage by mass of hydrogen in water? What is the percentage by mass of hydrogen in water? So in this case, we're going to go with the molar mass or the relative molecular mass of hydrogen as compared to the entire compound. So for example, hydrogen in this case is actually going to be, notice that you have 2 times 1, so it is 2. The mass of water is actually 2 times 1 for hydrogen plus this is 1 times 16 for oxygen, so it is going to give us 18. So when you're talking about the percentage by mass of hydrogen, well, this is going to be the amount of hydrogen, which is here 2, over the amount of everything, the total amount of everything here, which is 18, multiplied by 100%. And this is going to give us 11.1%. So this is the percentage by mass of hydrogen. Now you can also calculate the percentage by mass of oxygen. So how are you going to do it? Well, again, just use the same principle. Here in this case, oxygen is actually 16. And so water is still 18. So what you're going to do is the percentage by mass of oxygen is going to be the amount of oxygen here, which is 16, over the total amount, which is 18, multiplied by 100%. And this is going to give you 88.9%. This is the percentage by mass of oxygen. Now we can also say the percentage by mass of nitrogen in ammonia. So nitrogen is going to be 1 by 14, which is actually 14. Ammonia is going to be 1 by 14 for nitrogen and 3 by 1 for hydrogen. So this is going to give us 17. So the percentage by mass of nitrogen is actually going to be the amount of nitrogen, which is 14, over the total amount, which is 17, multiplied by 100%. So this is going to give us 82.4%. And so that is the percentage by mass of nitrogen in ammonia. Well, that's it for this video. Thanks for watching.